So first of all, thanks to Indo and ITDS for giving me the opportunity to present this talk in this conference. So I will mostly talk about a specific issue regarding the deriving these extremal surfaces in the context of holographic entanglement entropy for higher curvature gravities. So this is mostly based on this work with Menika Sharma, who is a postdoc at HRI, and also this is partially based on two of my earlier work with Anindo, Pratim and Menika. This is more or less the outline. So I will briefly go through this holographic entanglement entropy proposal, which is already beautifully introduced by Professor Myers in the Chandrasekhar lectures. So then I will straight away go to this Lewkowycz Maldacena interpretation, so called the generalized gravitational entropy method. One can think of it as some kind of a first principle derivation of this holographic proposal, and this method actually gives us a way to compute or derive the entangling surface equation. Also, on the other hand, we can generalize this Ryu-Takayanagi proposal for various higher curvature gravity theories, just like the world entropy. In principle, we can just extremize those modified area functional for these higher curvature duals and find out the extremal surface equation. But I will show that these two methods do not talk to each other. So, for certain specific higher derivative theories, what we get just by minimizing this higher curvature entropy functional will not match with what comes from this Lewkowycz Maldacena method, the generalized gravitational entropy method. So, at least to me this issue is important, because if you think about this Lewkowycz Maldacena interpretation as some kind of a derivation of this holographic proposal, so to make things self consistent, so we have to get around this issue, and I hope to impress this issue to the audience by my talk. And right now I do not have a definite resolution of these things, so I can always conjecture, and that we will do in this concluding part. So we know that in general relativity that black hole entropy is given by this famous area law. For a d plus 2 dimensional space time, the black hole entropy is given by the area of the horizon, which is a codimension 2 surface. That is why this dimension of here is d. And on the other hand, we have the Ryu-Takayanagi conjecture for the time independent entanglement entropy. So for a d dimensional entangling region at the boundary of a d plus 2 dimensional bulk space time, so the holographic entanglement entropy is given for this entangling region simply by the area of some codimensional 2 extremal surface, which hangs from this entangling region and penetrates inside the bulk. And from the CFT side, we usually compute this entanglement entropy by computing this reduced density matrix. So this is the map in our case. So now from this it is very evident that there is a striking similarity between this Bekenstein-Hawking formula and this Ryu-Takayanagi conjecture, at least for the Einstein gravities, both follows this area law. So one case we have area by 4 Joule Newton, and one case this area regulated by some UV cutoff. And this fact prompt many people to investigate this behavior, that is the connection between this entanglement entropy and the black hole entropy in some details, starting from this work by Raphael Sorkin, and in recent times by Bianchi and Myers, and lot more. So recently Maldacena as Lewkowycz has proposed this generalized gravitational entropy method, which actually somehow fills this gap between these two. So what they have done, they have basically generalized the concept of black hole entropy for the cases with no time-like killing symmetry. And we know when there is a U1 symmetry in the time direction, so the gravitational action can be interpreted as some log of some thermal partition function. This is the usual Gibbons-Huggins interpretation for in the context of black hole entropy. Now when there is no U1 symmetry, they say that we can still think of this gravity solution as some log of some trace of some unnormalized density matrix, which is here denoted by this rho hat. So from the field theory point of view, one can calculate this entanglement entropy by evaluating this quantity. This is the Rayleigh entropy. One can evaluate it for any integer n, then one can do it this analytic continuation in n, and then finally take this n equal to 1 limit to get back the entanglement entropy. And these things is evaluated using the so called replica trick, which is actually covered by Justin and Myers in their talk. So, I will just briefly mention these things here for the sake of continuity for my talk. So, to evaluate this quantity, this trace of rho to the power n, one can take multiple copies of the same field theory, and this is our replica space when we have to evaluate this quantity on this replica space, and we have to make the cuts where we impose the boundary condition. So, we have to go over these cuts. So, that will be our tau circle, and all these copies are stitched together in through this cut by appropriate boundary condition imposed on the field, and thereby it can be thought of as some sort of a n shaded Riemann surface. So, we are extending the tau circle to 2 pi n because we have to consider these n copies of the field theory, and this is for the integer n, and then we suppose that we can do this analytic continuation almost many cases. Then we do this analytic continuation in n to non-integer n, then finally we evaluate this quantity and take this n going to 1 limit, and that will give you that entanglement entropy. So, the handy formula for this entanglement entropy using replica trick is this. So, this is the log of this trace rho to the power n. This is evaluated on this replica space, and this is the trace of rho, which is the density matrix corresponds to this original field theory to the power n, and then one took this derivative with respect to the n and set n equal to 1 limit. Now, using the path integral representation of this density matrix, one can thought about this trace of rho n is equivalent to computing some partition function on this n shaded surface, which I denoted here by mn. So, Zn corresponds to the some partition function evaluated on this n shaded surface, but this surface has a Zn symmetry, as we know that this has a replica symmetry because the tau range of the tau integral goes to 2 pi n. So, this manifold will have a Zn symmetry, and this Z1 corresponds to n equal to 1 case. Now, at this point we assume that the holography exists, and then we can write this partition function as some exponential of some action I n evaluated on a bulk manifold B n. The point is that this bulk manifold B n is constructed using this boundary condition. So, you take the Mn as your boundary, and you construct a smooth bulk solution using this boundary, that is you are actually extending this replica symmetry on the boundary inside the bulk. So, and the denominator can be thought of as some e to the power n times I1 is the n equal to 1 solution with the manifold B1. So, you plug this formula into this, and finally we get the entanglement entropy expressed by this relation. This is what we get more or less from this concept of generalized entropy. So, this I n will correspond to a dual geometry with a periodicity in time 2 pi n, and if there is other matter field present, so they have to satisfy the boundary condition. So, we impose the periodic boundary condition on them, and one can visualize this I n as some kind of a regular geometry. So, this is the famous figure like diagram. So, when there is a Zn symmetry, that is by this some curved cycle represented here, and we are extending this smoothly inside the bulk. So, this corresponds to a regular geometry. Now, we have this second piece here, which is n into I1. So, I1 corresponds to some action for n equal to 1 case, but there is also a n there. So, for the I1, the tau integral goes to 0 to 2 pi multiplied by this n. So, one can thought of this as equivalent to doing the tau integral from 0 to 2 pi n. So, that means you are restricting the n equal to 1 solution the periodicity to 2 pi n. So, thereby you introducing a conical geometry inside the bulk, but this is not a real conical geometry, because this is just an interpretational issue. One can think this solution like this way. So, but we have to cut the tip off, because we do not want to the singularity coming from the cone to enter in our calculation. So, equivalently this picture can be thought of as difference between these two terms. This is a regularized cone, we regularize the tip of the cone, and it is generally a optional configuration. So, it need not to have to satisfy any kind of equation of motion. So, minus the tip of the cone. So, now we plug this back in the entropy formula there. So, we get a term like a difference between this smooth solution minus this regularized cone. So, there are 1000 ways to regularize this cone. So, but one can always choose parametrization such that the difference between the smooth solution and the regularized solution differ by order n minus 1 term. So, this is something like this. So, this is the smooth solution minus this regular solution. So, they differ by order n minus 1, and this thing is proportional to the equation of motion. So, this contribution actually vanishes if we impose the on shell condition. So, the remaining term is order n minus 1 whole square, and from this formula it is evident that only the order n minus 1 term will contribute. So, these two do not contribute in the entropy formula. So, the only contribution comes from the tip of this cone. So, we have to regularize this cone properly such that to make this total gravitational action finite, we do not want to actually spoil our calculation by introducing a conical deficit. So, this conical singularity appears because of the artifact of extending this replica symmetry into the bulk. So, now what we have done, we have extended this conical symmetry, that is the Zn symmetry, the replica symmetry, that is the Zn symmetry which the boundary manifold has extended into the bulk, and now we can thought of this in some other way. So, we can orbifold this bulk spacetime by this symmetry. So, it will result in a conical spacetime, and we have orbifolding by a Zn symmetry. So, it will have a set of fixed point, and they will form a codimension 2 surface. So, that codimension 2 surface will be near this tip of the cone. So, when we are saying that we have to evaluate the entropy formula just near the tip of the cone, that is what we are doing. We are doing that, we are evaluating that entropy formula on this codimension 2 surface, and the claim is that in n equal to 1 limit, that particular codimension 2 surface actually give us the extremal surface. Yes. No, that fixed point will form a surface like here. So, the yes, so something like that, that is a, this is a standard picture. So, at each point we are introducing the conical deficit on this extremal surface. So, you can think at this the conical deficit here, and you can think of it as some kind of a codimension 2 surface is sitting, which is this surface. And actually the problem become to find the tip of the cone, which is the which is actually translate in this picture is problem of finding the location of this surface. So, at each point you have this conical singularity. So, okay. So, to repeat again that we have to evaluate that entropy functional on the spatial codimension 2 surface, and to find the location of this codimension 2 surface, that is the location of this tip of the cone in this picture, one need to satisfy the bulk equation of motion near the conical singularity, and because of this conical singularity, we will get all sorts of divergence in the equation of motion, and we have to demand that the bulk equation of motion still satisfy setting all the divergent components of the equation of motion to zeros simultaneously and consistently, and that will determine the correct extremal surface equation. So, once we get the extremal surface equation, we can solve it and evaluate the entropy function on that surface, and we get the correct entanglement entropy. Now, to make the motivation one more time clear at this stage, so one of the acid tests for this holographic entropy functionals will be that the extremal surface equation coming from minimizing them should match with what comes from this generalized gravitational entropy method. So, and we will see for a certain higher derivative theory this will not work, and this is the main issue of this talk. So, I just want to focus on the issue to bring up this apparent mismatch between these two methods, and we will see how that will arise. So, before starting we should parameterize the cone. So, it is written in the complex coordinate z and z bar. So, in terms of Cartesian coordinates, z equal to w1 plus I w2 and z bar is the conjugate of that. This is the 2-dimensional part of the cone, and this e to the power 2 rho factor actually mimics the conical singularity. So, this rho is defined here. So, this becomes just the z bar whole to the power epsilon. Epsilon is the conical defect parameter, the angle defect, which is defined as the n equal to n minus 1, and we can then write the metric by Taylor expanding the metric around z equal to 0 and z bar equal to 0, just what we do in GR to write a metric around a point in the Gaussian normal coordinate. It is very similar to that. So, we have shown here up to terms order z square. So, this R denotes this transverse direction, which is here. Here we are dealing with a codimension 2 surface. So, there are two transverse direction, so which is 1 and 2, and we denote this x1 as z and x2 suppose z bar, and we write the metric order by order expanding around z equal to z bar, and this is the most general form up to this order z square. So, we can immediately see this Kij is the well known extrinsic curvature, which is defined as something like this in this case. So, sigma is the surface characterizing by g over 0 or w1 w2 equal to 0 in terms of Cartesian coordinate, and so it has a transverse direction because this is a so it no Dustin. So, this follows from a general definition of this. So, we have two normal corresponding to this transverse direction. So, this has a secret index which corresponds to the transverse direction. We denote here with R. So, corresponding these two normals, we have two extrinsic curvature. But at this stage, one can think of this one of this W2 as some time coordinate in the Cartesian, like dx plus dt square, and we will assume that this metric surface metric is time independent. So, z equal to z bar, and from this we will say kz equal to kz bar. So, this assumption I am making to make this presentation compact, but what I will say is true even if you do not make this assumption. So, it is just for the convenience to set these two extrinsic curvature equal to 0, and indeed for the ADS case when you perform this computation for the t equal to 0 slice, we get just only one extrinsic curvature. The extrinsic curvature in the time direction actually vanishes. So, now as I have said, the bulk spacetime has a Zn symmetry, or orbifolding by this symmetry leads to a fixed point with a codimension 2 surface with a conical deficit, and the entangling surface can be identified with this codimension 2 surface in n equal to 1 limit. and the surface is characterized by these two conditions, this W1 and W2 to 0. Now, first test this proposal for the Einstein gravity as a warm up. It is a very simple theory, and this is the well known Einstein equation. So, we will solve this equation near the tip of the cone. Then now we have to take two limits. So, there is a two parameter epsilon and z bar. So, we have to take z bar goes to 0 and epsilon goes to 0, but we have to take the limit in a particular fashion. So, to extract the singular piece from the bulk equation of motion, we have to take this z goes to 0 limit first, and it will give a singular piece only in the component of z bar and the z bar zz. So, this is shown here, but if one take this epsilon 0 limit first, that is physically this corresponds to the fact that we are just turning off the conical singularity, and then we will not get anything, because this whole game depends on this introducing this cone inside the bulk. So, we have to first take z equal to 0 and then take epsilon equal to 0, and so while taking this limit we assume that there is a small but finite conical singularity. So, we extract this divergent piece from the equation of motion. So, now according to this prescription or derivation, what one wants to call it, so we have to set it to 0. So, we have condition coming from here, which is the trace of extrinsic curvature to 0 for this Einstein gravity. Now, we see what comes from directly minimizing the area functional, which is the suppose this area functional is just the root h is the induced metric on this extremal surface, and this induced metric can be related to the bulk spacetime by this relation. So, a variation of this induced metric is related to the variation of this tangent vector, because this tangent vector is defined like this way. So, this is capital X are the embedding functional, which actually knows about the properties of the surface. So, we have to vary this, because we are varying this x. So, after doing all this, we get this variation in tangent vector written in this form, though zeta is some small variational parameter. So, we plug this back into this area functional, and we get this variation of the entropy functional like this, and we immediately see that we are getting the same condition, which is the trace of extrinsic curvature to 0. So, for the Einstein case, these two method actually matches perfectly well. So, now we will go to this higher derivative gravity theory. We will consider the R square theory, and this is sufficient for bringing all these main issue. Recently this entanglement area functional for a generic higher derivative theories containing only the polynomial of curvature tensor was first proposed by Dong and Camps in 2013. They have proposed this formula, and recent time this formula has been generalized for more general theories containing the derivative of Riemann tensor in this work by Ronjin Miao and this other person. So, to derive this formula, one actually start with this R square action. So, for simplicity I will consider 5 dimensional. So, R square action. So, this will have the curvature polynomial. So, you just evaluate on this conical spacetime and pick out the n minus 1 contribution from this total action, and that will actually give you this area function. This thing. Then to make this functional work, one has to perform this functional differentiation, which is easy to perform if you have a computer. Also you can do it by hand, and then we can resulting thing we can rewrite in terms of the surface quantity by using this various relation. At this point these details are not important, but just to get a flavor how this area functional works. So, I have just listed these equations here, and this Q is actually the second order expansion of the metric with respect to these two transverse direction, which is denoted here, and this Q alpha is a number defined, which counts the number of these Q's plus 1/2 these K's and these two specific component of the Riemann tensor. I will show what actually they are related to in terms of the metric component. So, at this level it seems quite artificial, but yeah, but this passes the basic first test of the entropy functional, that it produces the correct universal term for any general arbitrary surfaces. So, now the next question is, so if we try.
So, this formula, so I know you explained this to me once, but it seems like you only get k square.
Yes.
You never get, so even if you have.
No, not k square, not k square. So, point is that, so this is the term, right. So, what you are saying that this is true only for R square theory, because R square you have the R square term only. So, you just do this derivation, you just get a number and the k square just hangs around. So, if you suppose you have R cube theory, the R cube theory will get a R, then you expand the R using this. So, implicitly these are hidden in that quantity. These are all dimensionally k square. So, for example, this R p q I. Yeah, but nabla k occurs in this formula actually. Means there is some scaling means argument why means using that they are getting this extra piece, but that details as of now right now is unimportant. So, we can take this area functional and see what we get by minimizing this area functional, and if that is matches with this Lewkowicz-Maldacena method. So, this is the wall term and this is the extra term, and we see that this will vanish on a bifurcation surface. So, on the horizon this will give the correct black hole entropy, which is the world entropy, because on the bifurcation surface this extrinsic curvature goes to 0. And suppose we start with the R square theory, the Lagrangian is shown here. This is the Einstein term, this is the cosmological constant, and this is the R square part, and this is the R square couplings, this is lambda 1, lambda 2, lambda 3, and for this the Dong's prescription give this formula, and actually this formula is not very nice, because you can see this is not intrinsic quantity defined on the surface. K's are the intrinsic K's, and these R's are actually the bulk Riemann tensor contracted with the normals corresponding these two transverse directions, and this is the bulk Ricci scalar. So, this was actually first conjectured by Futsayev, Sorokin, Patrushev using this so called squash cone technique, and Dong using his generalized prescription can successfully reproduce this formula. So, before going to the most general R square case, we specialize for the Gauss-Bonnet gravity. So, we set this coupling to this value, and then we see that there are some remarkable simplification occurs, because we have this very nice identity, the Gauss-Coracci identity, and all these terms will in this area functional combine with each other to give you the intrinsic scalar curvature defined on the surface. So, this reduces the famous Jacobson-Myers functional, and we will consider we can extremize this functional, and obviously adding the Einstein piece to it. So, we get this full extremal surface equation just by directly extremizing this function. This first two term coming from the variation of the h, and the second term is coming from the variation of the r up to some total derivative term, which we can always throw away by adding a Gibbons-Huggins term to this area functional. So, let us see how whether we can reproduce these from the generalized entropy method. So, we evaluate the full Gauss-Bonnet equation of motion, and the Gauss-Bonnet equation has this simplicity that it has a two derivative equation of motion. So, near the conical singularity, and we extract all these divergences here.
So, if you go back to the
Previous.
yes, sir, I have asked you this. So, is this invariant under field redefinition in the Gauss?
No, actually point is that if you take so I know what you are saying, that may strengthen my claim. So, if you take this Gauss-Bonnet parameter perturbatively so small, So then you can obviously do a field redefinition and make the R square theory to Gauss-Bonnet theory. But you have to neglect terms like order lambda square.
No, I'm not talking about any lambda or lambda square term. I'm just asking. I mean, usually we can make.
But that is for small couplings. Means
So you're saying that you start off with Ricci scalar, start off with Ricci scalar, and then you do a field definition metric going to metric plus epsilon times Ricci scalar, say that. Then actually you are going to introduce higher derivative terms in the original action.
Yeah, but then
Actually itself is not invariant and field definition. It's only invariant up to a certain order and perturbation expansion.
yeah, but that's fine. But I'm asking is the entanglement entropy same after the bulk redefinition?
Perturbatively, yes.
It's the same.
Yeah, perturbatively you will get.
But it should not be same, right? Because it's like a change of scheme. So only the non-divergent terms will be the same.
no, but at the order lambda you will get just Gauss-Bonnet that will correspond to the Jacobson-Mars. Order lambda square you will get some extra terms.
I want to understand your question. So you're saying that you start off the bulk action. You do a field
Yeah, there is some higher curvature theory in the bulk.
Yeah.
And then you have this formula for the entanglement entropy.
Yeah.
And then the question is that, I mean, if I now make a field redefinition.
At the level of the bulk action or the
No, he is saying that at the level of entropy.
bulk action.
Then like the value of the entanglement entropy, does it change or?
Yeah, it will change.
Because the coefficient of the logs will not change.
So it won't change perturbatively. So I think he wants to treat these lambdas. As of now, he wants to consider order 1. He doesn't want to treat them perturbatively.
No, I'm asking this because if you are comparing like two different answers for the entanglement entropy,
Means,
just related, like it should, because it's like a change of scheme.
change of scale.
Yeah, I think you do that.
And so we minimize this entropy functional and we get this surface equation, and we will try to derive it from this generalized entropy method. So we evaluate the Gauss-Bonnet equation of motion near the conical singularity, and we list all possible divergence term in the component of the equation of motion. So to remind that this rho e to the power rho is v bar whole to the power epsilon. So this is a divergent term, but this is subletting compared to this leading term. Also we get this divergent term in this equation of motion, and now we have to set all these divergent term simultaneously to 0, and this proved quite tricky in this case of Gauss-Bonnet gravity. So for simplicity, first start with the limiting procedure as in the Einstein case. We take the z equal to 0 limit first, and we specialize to a ADS background, then we using the Correspondence identity which is this. So this divergence in this sometimes it is working, sometimes it is not. So so divergence in this Zi component actually vanishes using this Correspondence identity, and then we can also show this Q entering here is related to the square of the extrinsic curvature that will kill a portion of the divergence in the Ij component, but we will be left over with this divergent term. So the remaining divergence are in the Zz component after doing all this, and in the Ij component, and if we take Z going to 0 limit, so we have to set this one and to 0, setting this thing together with the Einstein counterpart leads to this surface equation which just comes from this Jacobson-Myers, but we have this extra condition here, and this condition are basically similar because if you dot it with the Kij you will get this. So, this serves as some kind of a constraint over this equation of motion, and the system become actually too constrained, and it is not expected that any general surface actually satisfy both of these equations. So, if you take a linear combination and you make some algebraic manipulation by replacing this R by Gauss-Corracci equation, you get this final form of the equation, surface equation, and this alpha is an arbitrary parameter which can take any value. So, the point is that is there any way out from this situation? So, we can thought of this limiting procedure as some kind of taking limit of a two function of a two variable. This is the epsilon and z, and we can from this two dimensional figure we can show that there are infinite way of taking this limit.
Right, so each of these choice that gives you different values for the entanglement entropy.
No, this is not even at the level of entanglement entropy. This is at the level of surface equation. Once you get the surface equation, you are getting different surface equation. So, but point is that if you just concentrate on the universal part, so for all these choice.
Oh, okay. I mean, then, so they must be related by change of scheme, right?
No, but this is a theory, same theory, and you are getting different surface equation depending on the choice of the limit. No, the point is that if you concentrate, if you want to concentrate on the universal part, it is fine, but the but the thing is that this problem will be become more clear in the R square case, because what goes in the derivation of this liquid is Maldacena. So, you are actually evaluating the bulk quantity on this cone, which is supposed to come from some satisfying some bulk equation of motion, and on the other hand you are saying that okay, there are some inconsistency, you can set all the component to bulk equation to 0. So,
saying that you won't be able to satisfy the bulk equation from motion?
Yes.
Unless and until K satisfies some extremely restricted condition.
By bulk equation motion,
There is a corresponding.
There is some curvature. Yeah, higher curvature equation.
So, the prescription is to evaluate those.
yeah. But the thing is that only thing which always confused me is that I mean, whatever you do, you always get the same universal part for the entanglement entropy.
Yeah, that's true, but then you shouldn't think of like coming from this Maldacena liquid type of formula where you are supposed to evaluate this on this thing on a on shell equation.
Helps you identify the two saddle points. Just a little bit away from n equal to 1. So if that doesn't work, then you don't have a two saddle point. So there is no
Just away from say if I have n equals 1 plus epsilon, then anyway there is singularity in the path.
yeah.
So that how I mean that also can influence in how seriously you can take.
No, but the logic for the generalized entanglement entropy was that you can satisfy the bulk equation of motion. That helps you identify the two saddle point, and you use that to compute the entanglement entropy.
Then you have this all old Forsyth derivation. There you also have this singularity inside the bulk, but to continue that, I am saying that infinite choice of limit here. So, one is just go through this y axis. So, that is the epsilon, you take the epsilon equal to 0 limit first, that is the turning of the conical singularity, that will give you nothing. So, because this whole game is dependent on this cone. Now, we can take this z equal to 0 limit through this axis, and that will give this over constraint equation, and one can always think of choosing some different path like this shown in this green color, like z equal to epsilon path. If we choose that will give you this equation, but with alpha equal to 0. So, we get just 1 minus 2 f infinity lambda into k. So this is actually the condition which will come if we just minimize the world entropy part of the area functional, not the full entropy function. And but still there is a way out. So we can take the limit as mentioned in this red path here, which is analogous of setting this epsilon by z, this quantity is some small quantity, inverse of some small quantity, this 1 by epsilon hat, and you demand this z to the power epsilon is going to some epsilon hat to the power 1 plus b, and actually this has shown for this v equal to 0.1. So this is the z to the power 5.1 is these things. So we get z to the power 2 epsilon by is equivalent to z by epsilon whole to the power 1 plus v, and v is greater than 0. So it is become easy to see here that if you take the z equal to limit first, that this will just go away. So all this subleading divergence will go away if you engineer this limit in this way, but only this term will survive, and setting that part will give you exactly the required surface equation. So Gauss-Bonnet, there is a way out, but now we will consider the most general R square theory. So this lambda 1, lambda 2, lambda 3 can take any value. So we can extremize this area functional and derive this surface equation which is mentioned here, and we see now what we will get from the generalized entropy method. So this reduces to the Jacobson mass functional by using this Corracci identity and the Gauss-Corracci identity simultaneously, and then we evaluate this bulk equation motion for R square theory, which is a general 4 derivative equation, and for this we need the third order term also in the metric, which is shown here, and we can identify all these coefficients by calculating some bulk curvature quantity and relating them to that. Especially this coefficient is here, you can see related to the derivative of the bulk Riemann tensor contracted with the normal. So we can solve, we demand ADS background, and we can solve all these coefficient by computing all these curvature quantities and derivative of it, and we get this W of this form. And I should mention what is this f infinity here. So f infinity satisfy this relation. So we list again all possible divergent term. One thing is that this W itself contains a e to the power 2 rho factor in it. So that will be important. So so again the ZZ component has the divergent term, but there is a new divergence which appears for the general theory. You will see that this vanishes actually if you put the Gauss-Bonnet value in it, and this W will be uplifted because there is a hidden e to the power 2 rho term in it. So it will contribute to the epsilon by z term. Also there is some divergence in the ZZ component which was not there for the Gauss-Bonnet case, and we have the Zi and the Ij component also. So we take this limit same as before, that is z to the power 2 epsilon by z by epsilon whole to the power 1 plus v, because we know that for the Gauss-Bonnet case this works, and obviously if we put the lambda for those particular value it should reduce to the Gauss-Bonnet case. So we take the same limiting procedure. So this remove almost all the divergences, but it but the ZZ component has this extra piece, this 1 by epsilon square 1 by z square divergences, which is goes as some z to the power epsilon whole to the power v minus 1 as v is less than 1. So this actually contributes. So now we set this leading this part of the divergence to 0 using this all this formula for the metric coefficient on the area's background. We get this surface equation and see that we are almost there, because this surface equation and what we get for minimizing the surface equation for the R square entropy functional differ only by this k cube term, which is actually subleading correspond to this RK type of terms. But we have to also satisfy these extra conditions. So we set them to equal to 0, and we see that this cannot be satisfied for any arbitrary value of lambda. It is only being satisfied when this lambda takes the Gauss-Bonnet value. So there is some problem lying here. Also the ZZ bar component has this kind of a divergence, and this W contains a secret factor of e to the power plus 2 rho. So, it will cancel this and W will have this epsilon type of Z divergence. So, we have to set that to 0 and that means we are setting W to 0 and there is no reason to set this component of the metric. It may be true for some particular space time, but in general it may not be true. So, there is all this mismatch. So, it seems that for the Gauss-Bonnet case these things work, though it is too artificial. So, we have to engineer the limit in this particular way, but for the general R square theory whatever we have done up till now nothing seems to work for there all, and so these mismatches are still there. So, as we are getting these mismatches, so we do not want to leave any stone unturned for finding a possible justification for this kind of a area functional. So, one of the interpretation I will briefly mention, it has been pointed out by Lewkowycz and Maldacena that this extremal surface equation for the Einstein gravity is same as some kind of a surface equation for a cosmic string which sweeps to the space time, and we know that this the action is just the Nambu-Goto action and we extremize it and we get this trace of extrinsic curvature to 0. And Zedong has actually extended this argument for the higher derivative case, which he referred to something called a cosmic Brane method. So, this cosmic Brane produces a space time with a conical singularity, and this Brane we will think about localized at the tip of the cone, that is at z equal to z bar, and it extends in the y1 direction. So, we have now total action as or higher curvature of it plus the Brane action, and this is the defect parameter. So, you can think of it in epsilon tends to 0 limit, you can think of this as a probe Brane which helps us to find the actually correct location of the tip or the extremal surfaces. So, key idea is that the bulk equation of motion now will have a non-vanishing trace tensor because of this Brane action, and as the Brane is localized in this ij direction, it will have a non-vanishing trace tensor only along the ij direction. As this is a localized object, we will have a delta function as the trace tensor. So, we solve the bulk equation of motion in this conical background, we identify the delta function and then we interpret that as some kind of a trace tensor for this Brane action, and using this famous formula for the trace tensor, once we identify this we can get this S, and this S is supposedly the entropy function. So, Gauss-Bonnet theory it works very fine. So, Gauss-Bonnet we get the trace tensor expansion like this is the delta function defined like this way, and in our way of taking limit this part is goes to 0 and we will left with this part only, and we can see that this easily comes from this Jacobson-Myers functional, and all the other bulk component of the trace tensor is 0. So, this is actually consistent. Now, for the R square theory we play the same game with this thing and we get this complicated stuff. So, we can see this middle block goes to 0 in our way of taking the limit because this is a factor of e to the power 2 rho outside, and we will left with this upper and the lower block, and this actually matches exactly for the R square area functional predicted. So, this seems to be good, but the point is that we also get delta function divergence in the ZZ and Z bar component of the trace tensor, which we should not have because the Brane is localized along the ij direction. So, one has to somehow take care of this divergence and give an interpretation to this. So, obviously, in any attempt to actually justify the area functional using this cosmic Brane method has to take into account of this extra divergence for generic high derivative theory, in our case the R square theory, and one should have to interpret this why this divergence is coming and take that into account. So, to conclude that for Gauss-Bonnet theory this both sides of the story works very fine. So, but though this limit taking procedure is quite artificial, but there is some sort of way out, but we do not know what is the physical significance of this particular way of taking the limit. So, the for more general theory for this R square theory obviously we have a mismatch, and these two methods do not talk to each other. So, there may be some way out. One way out is that there are some subleading terms in the area functional which are missing, which can cure this problem, and also this area functional is supposed to satisfy this strong sub-additivity, and also for the Gauss-Bonnet gravity we know that this area functional satisfies the second law, and so this combining these two checks, one can actually constrain the parameter space significantly and derive this area functional using these two conditions. So, one more possible way is to this some sort of a possible modification of this Lewkowicz-Maldacena method, or a last possible way out is to add some matter sector to this gravity sector. So, it will correspond to some trace tensor, and hopefully if one can work out this solution for this matter sector near the conical singularity, it will actually help us to cancel this extra divergence which we see for this general R square theory. So, that is all, and thank you for listening to my talk.